Okay, so we're going to go to lecture. I haven't. So that was remind me when I finish. I meant to look at it and I just got distracted. Thank you. Okay, so here we're going to start. We're going to start with LeChatleir and doing fun stuff with it. Okay, LeChatleir is a reversible reaction. It has to do with reversible reaction. That's where you see this kind of arrow. Okay, shh, guys, get your notes out. Go. We're on the notes. We're going to finish the notes today. I gave you the review so that if you're on task and where you should be, that you have something to do on the board.
Wait,
Next one.
wait, is this? Oh, wait, never mind.
Okay, guys, we need to focus. I know you're excited to see each other after break, but let's get going. We have to be done with chapter 6 before the next one.
Wait, it's not chapter 6 now?
Huh? We're still on chapter 6 next. So we have 7 chapters next. Okay, focusing up front. Voices are off. I believe so. That's it. So it should be back. Okay, so systematic equilibrium is when the rate forward is the rate backwards. Remember last time we did the water? You guys said, oh, the water, the big side's they're gonna be equal, and that's equilibrium. When we did that experiment, it didn't end up at equal levels, right? Because what happened is it was the same amount going backwards and forwards, it's not the level. So that's what you got to get in your head. It's not the level, it's the amount going forward and backwards that makes it at equilibrium. Okay? So that's why I had to do that water thing. So it gets in your head, it's not making the same level, but it's the same amount that's moving backwards and forwards in the small beaker and the big beaker. Okay? That's what equilibrium is. So that's definition then is the equilibrium is the rate of the forward reaction that was represented by the beaker going from the reactant to the product is equal to the rate going backwards from the product to the reactant. So the amount in both beakers was the same. Okay? The net concentrations of the product and the reactants do not change. So that's why we had to have it at the same level for 3 or 4 times. Right? That means that's the concentration. They weren't changing. Okay, so some definitions that we need to know. Position of equilibrium. Is it more towards the reactants or is it more towards the product? That's the position of equilibrium. Do I have more water in my reactants or in my products? Okay, that's the position of equilibrium. Equilibrium expression, I'm hoping I will let you write, because earlier it wouldn't. Yes.
Do you have any extras of the notes?
It would be in the blue file cabinet there. The equilibrium expression is a KEQ, what we call KEQ. That's an equilibrium, that's the definition of what equilibrium expression is. You always take the products over the reactants. So I'm going to take my products and I'm going to say the small letters represent the coefficients. So I would say my concentration of C to the power of little c times the concentration of D to the power of little d divided by my reactants, the concentration of A to little a times the concentration of big B to the power of little b. That's what we call an equilibrium expression.
And these are multiplied together, right?
They're multiplied. So what's included? Gases and aqueous. What's not included is solids or liquids. They drop out. So if I have a solid or liquid, it is not part of my equilibrium expression. Okay? So you should be able to take any equation, balance it, write me a KQ. Yes?
Can I go back to slide real quick?
Okay, we okay? Everybody found out where we're at now in your notes? Again, I will put this up on your canvas so you can see it. Okay? Alright, so this is really important. Only gases and aqueous can be in the KQ. Okay? Usually when we use brackets, it means concentration. That means it's an aqueous solution. If it's not, we sometimes use what we call pressure, and that would be pressure of C to the, we use parentheses, C power times the pressure of D to the D power divided by the pressure of A to the A power, and pressure of B to the B power. For the most part, this right here, you don't really need to know. If you know this, you've got it. Okay? As you go up in chemistry, they do distinguish between concentration and pressure, but at this level we don't. Okay? All right. Going forward. Oh, see, I've got other stuff in there already. So let me erase real quick. Forgot I had it coming in. Okay, I had it nice and pretty in here, I wrote. All right, has everybody got this? So KQ is what we're basically going to be concentrating on, but don't get thrown off if she happens to throw a KP in. Same thing, we're just using pressures. Because usually gases are new concentrations. Okay, so what does it KQ mean? If KQ is equal to 1, that means the forward rate and the backward rate are the same. My reactants are equal to my products in concentration. If the KQ is bigger than 1, that means at equilibrium I have more products than I have reactants, because this is the basic setup. I have more products than reactants, so I've got a KQ that's bigger than 1. If my KQ is less than 1, that means I have more reactants than I do products, because I'm going to get a number that's smaller than 1. Okay, I'm going to get a fraction. So you need to be able to verbalize this. Okay, so she'll ask you if my KQ is 1.2 times 10 to the 15th, what does that tell me? So the equilibrium lies towards the products. I have more products present than I do reactants, so it tends to favor the products. If the KQ is 0.10, my reaction favors the reactants rather than the products. Okay? All right, so now we're going to write some KQs. Very simple. These are all gases. We're still going to put them into the aqueous. We could write it as P or KPs, but I'm just going to do KQs because that's how she's mostly going to show you it. So always remember products first. So I'm looking at the product side. I'm going to go concentration of, I'm just going to make sure, nope, I did. Okay, concentration of CO2 to the 4th power, concentration of water to the 6th power, concentration of C2H6 to the 2nd power, and concentration of O2 to the 7th power. That's all you have to do.
Would it matter which one is out of the second one? So like, I mean, if they go both ways.
So you always want to do it as it's written.
You keep it up.
So reactants will be on your left, products on your right,
So
even
write-
though it goes both ways.
So write this like the products first. Isn't it?
Products always go on top,
Over the-
over the reactants. Okay, would you really quickly do the next two and see if you can get it right? See if you can write the KQ for the next two. I gave you an example with one of them, and I'll write how you would do KP. It's just basically the same, it's just different.
Could you write this as a matrix?
You wouldn't want to.
Well, I'm just thinking of larger equation. Okay, never mind. You're correct. You basically what you're doing right now.
So this right here is it because this one's pressure. She might write it like this, but she also might write it like this. No, because it's multiple choice, right? So I'm just showing you how it would look both ways. Okay, this one is because it's gas, it would do the pressures. So both of those are, the more correct of these are this one, but you might see her write it this way. Because at this level, we're not going to necessarily do different. Okay? All right, somebody I think they got the bottom one, or the second one down? Yep.
Is it like the bracketing and then like N2 and then a 2
Okay.
and then another bracketing and then H2O and then a 6 and then another bracketing and then NH3 and 4 and then another bracketing and O2 and 3.
Yep. Now again, since this is pressure, we would write it this way. Oh, thank you. I didn't see that was a liquid. Oh, hello.
Wow.
So this one right here shouldn't be there because that's a liquid. So we don't write liquids. No liquids, no solids.
Oh wait, really?
That was the first question.
There were no liquids or solids in the first one.
Gas.
If it's a gas or aqueous, then we write it.
Wait, but it's like the same one. Like no liquids.
So the next one I can
Water vapor. Isn't there
So the next one's all aqueous, so we write all of them.
Isn't there a liquid in the first one?
Gas, gas.
Oh.
So I have to look at the states. Okay, the last one. So this could also be written as Kp equals pressure of nitrogen to the second power divided by the pressure of ammonia to the fourth power times the pressure of oxygen to the third power. It's the same thing, it's just, yeah, one they just say it's pressure because it's gases, the other one brackets mean concentration, like LeChatleir.
Wait, you can only do pressure with gases
Right,
or aqueous.
aqueous with concentration. So, but what I'm telling you is on some of the questions, on the test, she's not consistent. So, no both ways. Does that make sense? It's basically the same thing if you just remember to set it up. Okay, bottom one, what are we looking at? KQ here, because it doesn't have gases, it's all aqueous, so there's only one way it should be written. Concentration of FeCN 6 with a -3, and it goes to the 1 power, so I don't have to write it. Concentration of nickel plus 2 ions, and it's to the 1 power, and then concentration of CN minus to the 6 power. Yes.
So we don't have to balance these ones?
As long as they're already balanced, you're good. These already have numbers in here that tells me they're balanced.
But double arrow would technically mean they're balanced, right?
No. That just means that both reactions go both ways.
Oh.
So the numbers in front, when you see that there's numbers in front, that will tell me that it's balanced.
Was she gonna give us some that aren't balanced?
You'd have to balance them first.
But is she?
The review that I gave you is basically the test. You just have to go through it. Okay? Okay, going forward. Maybe. Thinking. Okay, so now she could give you the K and ask you to write the equation. That's not hard, right? Because my reactants are on the bottom, my product's on the top. So for this one, it would be H2 plus I2, and since these are both concentrations, it would be AQ going to 2 HI AQ. And I'm done. Brackets are AQ. If it says pressure, it would be gas.
Can the arrow go both ways?
Oh yes, I should have the arrow going both ways. Thank you. Okay, would you write the other two equations?
I didn't think
Just remember it's products over reactants. And the coefficient or the exponents are your coefficients. Yes.
How do you know if it's aqueous or a gas?
If it's brackets like this, it's aqueous. Which doesn't really make sense with oxygen. You have to be really cold, but we'll take it as is.
Well, yeah, so I know you should answer this question, but I don't know if it's aqueous, gas, or whatever.
So if it has brackets, that means aqueous. If it says PO2 to 7, that's a gas. So parentheses with P's are gas.
Now, if it's listed like that, could technically the products be missing something?
Yes, it could technically be necessary. So when you go to make it, or make the equation, then you gotta look and see what else could it possibly, is there something missing? Does it not balance side to side? Good question. Okay, so on this one especially, right, there's gonna be something missing. Bottom is my reactant, so CH4, aqueous, plus O2, aqueous, yields CO2, and I had two O2, so I should put 2 there. CO2. Well, I can see right now something's missing. Can you see that something's missing?
There's no hydrogen on top.
There's no hydrogen. So it has probably, I heard it, probably H2O, but it's probably in what state? Liquid. And then I would just look and say, oh, I need 2 of them, now I've finished the equation.
Would we have to like know that?
Yeah.
Okay.
Okay, but you're looking at the equation and you say, okay, there's hydrogen on one side, there's not on the other side, what could be missing? Yes.
Wait, so if there's a gas and an aqueous, what would we do?
So you can do something like this, where you mix them.
Oh, like that?
I don't know.
Okay? It's not really, because the units don't go together very well. We usually have to use pervnert, and we haven't got to pervnert yet to convert, but we'll deal with that later. Okay. Does anybody have the last one? B for the equation. Remember you've got what on the bottom? Reactants, right? So NO2, we know it's aqueous, and we know we have 4 of them. Plus, I know I'm going to have something because on the top I have a hydrogen. So I'm just going to put it plus something right now because I don't know what it is. On the other side I have 4 NH3s, which are aqueous, plus 7 oxygens, which is also aqueous. What am I missing? Sorry, I'm going to run out of room. That's already right there. What do you think I'm missing? H2O, good. And how many hydrogens do I need? I need 6. I need to put a 6 in front because I have 12 over here. So if I put a 6 in front, and this has to probably be a liquid.
So you basically just always add like
It's usually water or a solid like copper or metal that's dropped out. Okay? So it usually is pretty easy to fill that hole if you just look and say, oh, what am I missing? Oh, I need hydrogen and I don't have enough oxygen, so that probably is water. Okay? All right.
Wait, did you say oxygen is aqueous?
Yeah, but it's really a gas. Okay, so given equation, you've got an equation, is allowed to reach equilibrium. This is something she would give you on the test. Okay, so please pay attention. Okay, so she's given you the equation, and she's also giving you the concentration of each at equilibrium. And she wants you to tell what the equilibrium constant is for this reaction. So the first thing you want to do is take your equation and write your K cubed. So your K cubed products, concentration of NO squared times the concentration of CO2, no exponent, divided by concentration of NOCl squared. So first you write the equilibrium expression, then take and plug in. So my NO right here is 0.92. I'm going to square that. My Cl2 is right here, 0.20 molar. I can put molars in there. It's not squared, divided by my concentration of NOCl, which is 1.31 molar, and it is squared. Okay? Now, we'll plug that in our calculator, and we're going to get an answer. So, if you haven't got a calculator, some up here. We're going to be using them, so grab what you need. this squared times 0.2, so 0.92 squared times 0.2, give me answer, divide by, and then put parentheses, I would do parentheses around the bottom here. Parentheses 1.31 squared plus parentheses. What do we get? Now, second.
Yeah.
Okay. Alright, so what does this tell me? Remember what the K represent? What does this tell me about this equation? It's actually favoring the reactants more than it is the products. Okay, so it's not going forward. It's staying mostly reactants. Very few of it's going to products. So at equilibrium, where I've reached the point where the same amount's going forward and backwards, I have a lot more reactants than I do have products. That's what that tells me. Yes?
Why did you square the NO and not the CI?
Okay, so use the coefficients to tell me what its power is. Okay? All right, so here we go. Describe what you would expect at equilibrium. So here's a K. We've got 2.1 times 10 to the negative 6. What do I have more of? Reactants or products? What do I have more of? Yes?
This isn't on our notes.
I know, I just want you to pay attention up here. Okay, what do you have more of? Reactants. Whoops. Yes. So you have more reactants than products because it's less than 1, right?
Oh.
And you have less products. So she's going to have some problems on here. I want you to be thinking this through and not just writing down. Okay, here we have K is equal to 0.15. What do I have more of?
Products.
Good. What do I have less of? Okay, what about the next one?
More products.
More products and less reactants, right? What about the last one?
More reactants.
More reactants and less products. Okay, so being able to look at a K, you should be able to tell me what's going on with the reaction. At equilibrium, what's happening? Okay? All right. We get to what's called LeChatleir. So in order to use LeChatleir, a reaction needs to be at equilibrium. So think of our water thing again. We've now got it 4 in a row, and it's the same thing. How do I shift that equilibrium? So this is what LeChatleir's principle says. Once I have that at an equilibrium, in order for something to happen, something's got to change. I either need to add or subtract or do something with it. So LeChatleir says at equilibrium, when it's disturbed by a stress, when I apply a stress to a system that's at equilibrium, the system will react to counteract that stress. So think of a teeter-totter. We're sitting equal. We have the same amount of weight on both sides, and now somebody comes and sits down on one side. It's going to go like this, right? And in order to get it back up equal, I either need to shift these people closer to the fulcrum, or I need to add some more people on the other side, right? To make it go equal again. Otherwise, the teeter-totter is not going to teeter very well. Okay? So these are the 3 things that affect equilibrium. I can do a concentration change. I can take a bucket of water out of one or add a bucket of water in. I can do a temperature change. The temperature change will shift because heat can go in or out of a system. Pressure change. Gases are affected by pressure. So if I apply a pressure to a system that has gases, it'll go to the side that has the least amount of gas. Because when I squish things, they go to the side that has the least amount of gas. Okay? All right. So got a lovely little video here for you to be annoyed with. And hopefully it'll help you.
To and fro, forwards and back, simultaneous. It flows. Reactants becoming products at the same rate reverse goes. It goes forever, system closed. Nothing gets in or out. But once the system system's open, you might hear this shout. Stress, shift, changing concentration. Stress, shift, changing concentration. The LeChatleir is so much fun. Equilibrium shift for everyone. If you add reactant, collisions more between. It shifts towards the product side. Product increases seen. If you add a product, collisions will improve. The shift is toward the reactant side, and products are removed. If the concentration goes down, whichever one you choose, then the shift's the other way, towards whatever you remove. Stress, shift, changing concentration. Stress, shift, changing concentration. The LeChatleir is so much fun. Equilibrium shift for everyone. If you raise the temperature, shift endothermically, move away from the side with heat, and you will surely see. If you cool the system down, it's an exothermic shift. Select towards the side with heat, the temperature will lift. If you raise the pressure, the side with less gas will score. If instead you lower P, shift to the side with more. Stress, shift, changing concentration. Stress, shift, changing concentration. The LeChatleir is so much fun. Equilibrium shift for everyone. Stress, shift, changing concentration. Stress, shift, changing concentration. The LeChatleir is so much fun. Equilibrium shift for everyone.
Okay, so when you do this, the easiest, let me turn this back on. The easiest thing to remember is if you put the arrows in at the top, that you're putting something in, it will tell you what way you need to go, because if you come in on top, you've always got to cross the arrows, so it would shift this way. Okay? So if you're putting things in on this side, then it would shift that way. Does that make sense? So it has to cross the arrow. So if you put them in on top, that works. If you put them in like you're taking them out, so if I'm going out of this, it would shift across the arrow and out, so this side would get more. Okay, so I've got to fill the hole. When I'm shifting out, I'm like digging a hole, and I've got to fill it. Okay? So, easiest way to remember it, I know that was an annoying song, but if you watch the video as we were singing it, or as he was singing it, it actually went through it, I think, pretty well, and actually taught you what you need to know. So, you should be able to look at any reaction and be able to tell me anything about that reaction. If I took out CO2 here, if I took out CO2, which way would it shift? It would shift to the left, that's right. Okay, because it's got to go across this and come down to fill the hole. Okay, what if I added O2? Then I've got to still go across the arrow, so it's going to shift to the products. Okay, do you see what's going on? That means this side would decrease in concentration, this side would increase, even though I added O2. The final one hit equilibrium, the reactants would be less. What if I took out CO2? Right or left?
Right.
To the right.
To the right. That means I'm going to get more CO2 and less CO and O2. Okay, because I'm at equilibrium to start with. If I'm not at equilibrium to start with, I cannot use this. Okay, it's got to be already established at equilibrium. Okay, so it sort of goes through that down here. Let's look at another one here. Same equation, just doing different. If I add products, it's going to shift away from where I had it. I like to think about it. My dad was one of those people that would buy a big dump truck load full of stuff that you had to shovel, you know, the wood chips into the flower garden so they looked nice every year. And so there'd be this big dump truck that would come and dump, and we would scatter it around the yard. Okay? We also had a dog that loved to dig. And so guess who got to fill the holes? So if the dog dug a hole, I had to bring it from other parts of the yard to fill the hole. So to me, that made sense. However you need to remember it, I like to pile it in on top. Okay, if there's a big pile that's shoved here, then I've got to scatter it across the arrow. So I've got to take this and scatter it across the arrow. If my dog dug a hole, I've got to fill the hole. Okay, so that helps a lot. The last thing that we need to look at is the gases. Remember, two things, gases and temperature. So on this side, we have two gases. Can you see that there's 2 moles of gas? On this side, we have 1 and 2, so we have 3 moles of gas because both of these are gas. So this side has less than this as far as moles of gas. So if I increase the temperature, which way is it going to go? Or increase the pressure, which way is it going to go? If I increase the pressure, right or left?
Right.
Right. It goes to the side with the least amount of gas. So if I increase the pressure, I'm squishing it, it'll go to the side with the least amount of gas. If I decrease the pressure, it goes to the side with the most. Okay? All right. Here. If product is removed, it goes towards the product. Again, if you're making a hole, it's going to go towards the product, wherever you're making a hole. If I'm making a pile, it's going to go away from the pile, across the arrow. All right, now, they can do heat this way, or they can put heat in the equation. If it is a plus, what does that tell me? You're just going to put, like, heat's on this side. Okay? If it's a negative, then heat would go on the product side because it's being given off. So this tells me this is an endothermic reaction. I have to put heat into it to make it react. Put it on the reactant side. Do I have to show how much? No. I just need to know where the heat is so I can know which way it's going to shift. So if I take heat out of this equation, make it cooler, what's going to happen to the equation? It'll go to the left because I'm making a hole by decreasing the temperature, so it has to come this way to go fill that hole, right? What about if I increased the heat? Shift to the right, yep. So just remember, it's the same kind of thing. Okay,
Because the extra heat would favor the reactants.
on this one?
Yeah.
It would favor the product. If I put extra heat in, it would shoot it to the product.
Yeah.
Okay, so on this one, if they give it to you like this, the negative tells me what side is heat on. Product. So I just put heat here just so that I remember. And I say, okay, temperature increases. I'm making a pile here if it increases, right? Which way is it going to go? Left. It's going to go away from the pile. If I decrease it, instead, I'm just going to do a little squiggly. If I decrease it, which way is it going to go? It's going to go to the right, so it's going to come this way to complete it. I usually can change colors, but my board is acting really weird. Okay, now we worry about pressure again. This is another one, pressure, we already talked about it, but you only add up the ones that are gases. So if you have liquids, solids, aqueous, you don't add those up. You just look at the gases. So here we have 2 moles of gas, here we have 4 moles of gas. Depending on what side we need to go to, if we decrease the pressure, it goes to the side that has the most. If we increase the pressure, it goes to the side that has the least. Okay? These will be easy questions on the test if you can remember what LeChatleir is. Okay? 3 things: concentration, temperature, and pressure. concentration, temperature, pressure. That's the only things that can do it. And then it also affects only aqueous and gas. Okay? All right, so looking at this, if I add more reactants, which way is it going to shift? Go to the right, more products. If I remove reactants, goes to the left. If I add products, if I remove products, okay, really easy points, but don't get confused, okay? Just remember, if I'm adding in, it goes away from me. If I'm taking out, it goes towards me. Okay, fill the hole. Okay? All right, increase temperature. Good, because I'm putting stuff, increasing temperature here, it has to go this way. Okay, decreasing temperature. Increasing pressure. Or she could say decreasing volume. If I'm decreasing volume, I'm increasing pressure. How many moles do I have on the reactant side? How many moles of gas on this side? 4. How many on this side? 2. So I'm increasing pressure. Which side is it going to go to?
Wait, why not 3?
1 and 1, 1, and, or 3 and 4. It's going to go to the 2. Good. So she can write it, she can word it either way. Increase the pressure or decrease the volume. What if I increase the volume or decrease the pressure? Towards the reactants, right? Okay, so this is really easy if you get it. Really easy points. Okay? All right. Now this is being more specific. Number 1, if CO is added, which way is it going to go? Right or left? Right. If H2 is removed.
Left.
Good. I want you to all point with your fingers. H2 is added. H2O is added.
Right.
It's added. I'm adding it here. It's got to shift away. Okay. CO4 is removed. CO4 is removed.
Fill the hole. So right.
If I'm removed, I'm making a hole, right? You got to fill the hole. You got to cross over the line. Fill the hole. So it's got to go this way. Okay, volume is decreased, therefore pressure is increased. And I'm telling you both of them, but she'll only give you one of them on the test. Okay, volume is decreased, therefore pressure is increased. You've got to remember that.
That way, right?
So you have 4 on this side, right, and 2 on this side. Decreased. Volume is decreased, pressure is increased, so we go towards the 2. Okay, just think pressure's increases, squeezing it. Volume decreases, squeezing it. It's going to go down to the side that has the least. Okay? Heat is added. Heat is added. Which way? Stay with me, guys. Stay with me. Heat is added. Where's heat? Am I piling it in or taking it out? I'm adding it in, so which way is it going to go? Away from it. So I'm making a pile, I'm adding it, it goes away from it. Okay? It's going to go that way. It's always got to cross the arrow. Okay? That's where the heat is. So where you see kilojoules or where you say heat or where it'll have a negative delta H, that would be on the product side. If it had a positive delta H or kilojoules on the reactant side, that's endothermic. Adding heat to make it work. Okay, we got just a couple other things to go over. This is an activation curve. Very simple. Have we talked about this before? Okay, so just reviewing real quick. Reactants, you should be able to read off the activation energy of the energy of the reactants off a graph. You should be able to tell what the products are, and you should be able to take those 2 away and get delta H. You should be able to tell what the activation energy is. That, remember, is E of A. Going backwards, it's E of A prime. You also need to know if there's a lower thing shown. That tells me that it's a catalyzed reaction. So it doesn't take as much energy. That's like having a matchmaker. Okay? It doesn't have to be a nice smooth curve like this. It could actually go like this and come back like that. It could have many little wiggles in there, as long as it's lower. Okay? So catalyst is like a matchmaker, just get things oriented. Energy of activation, you need to be able to like label what it is. Reactants to top of the curve. Net energy of the reaction, that is the difference between I started and where I ended, also known as delta H. Potential energy is where you start. Potential energy of the reactants is where you started. Potential energy of the products is where the products are. Okay, just you need to know what they are so you can read it off a graph. Okay? All right, we're gonna blow by this really quickly.
What's the peak of that graph?
The peak of the graph is called the complex, the activated complex. Okay? All right, I'm going to blow away this one. We're going to come here. With our lab that we're doing next time, we're going to be working with LeChatleir. We're going to be working with how does heat affect, how does different things affect the reactions. I gave you a lab that we did with the petri dishes and the well plates and the filled canisters. Remember that one? And I let you change different things. This is sort of like what's going on here. We're going to have a reaction. And depending on what we do the reaction, it will shift the reaction one way or another. But this is a chemical reaction that doesn't end. The ones that we did last time ended. These are reactions that can go back and forth forever, depending on what I do. So this is a reaction that was pink, but if I add heat, it turns blue. If I remove heat, it goes back pink. Okay? So if the reaction above is cool, what's going to happen? What color? It's going to be pink. Good. Because I will be taking out heat, so it's going to come to this side. So she's going to have one that's colored like this. And she'll say, what color am I going to see? Okay, if Cl minus is added, what color am I going to see? So if I add Cl minus, it's got to cross the arrow. What color am I going to see? Blue. Okay, so this was pink. This is blue. If I add CO2, if I take away cobalt 2, then it will be pink. Good. Because I will be taking this out. So I have to go to where I fill the hole. Yes?
So when you're taking it out, it doesn't have to cross the arrows?
No, it has to cross the arrow. It's just the tail end of it had to cross because I'm bringing it over to fill it. Okay? So I always go, my arrow's coming down, so I have to go forward to cross it. My arrow's already going down, so I have to come over to get it. Okay. Make sense? Yeah. Okay, so looking at this one, again, this is another kind like she would have on the test. Fe3 plus is added. What color am I going to see? Blue? Good. Okay. Fe, or iron thiocyanide, is removed.
Brown.
I heard both, blue and brown. Which is it?
Blue.
So I'm removing this, so it's going to come towards it. So it's going to be blue again. Okay. If I add it instead, what's it going to be? Brown. Okay, so try and get it in your head. I found that if I do the arrows, I sort of see which way the arrow's supposed to come. So if I'm removing it, I always head towards that. If I'm putting it in, I always move away. Across the arrow.
Why would it be colorless? Because it's closer.
Which one's going to show?
Brown.
So be careful on that because if there's two that are colored on one side, it might mix and make a different color. So if I have a green and a yellow, or sorry, a blue and a yellow, it'll make green. If I have a red and a blue, it'll make purple. Okay? All right.
So then in that instance, what if it was a yellow and a blue, then we think like the answer would be green.
Green. If it was on one side, if they're opposite, then it would be either or. Okay, so here's another one. Cl minus is removed. Okay, I'm going to C, colorless. Heat is added. Yes. Heat is added, it's gotta come across the arrow. And this is removed, so it's gotta come across the arrow this way. So this is colorless also. PbCl2 is removed.
No, it'd be yellow.
Yellow. Okay, so you can see this is easy if you can get it in your head. Okay? Easy points. Okay, we did the LeChatleir challenge already with the buckets. That's why I'm going to blow by that. Next time we're going to do experiment 11. You need to make sure you're ready to do it. This is the precursor that we did together, but now we're going to work with reactions that are reversible. So in general chem, they do this reaction where it's not reversible. But now we're going to work with stuff that is reversible. We'll be playing with it. Okay? The test is going to be January 15th. That's the end of the semester. So I have given you the review. I have given you everything that you need to have. We're going to do the lab next time. And I've actually got it set up, so if you wanted to do the first part, if you've already got it written, you can go ahead and start it. The next 2 days in class will be the lab and help with the review. Okay, to get you all where you need to be. Remember, all learn smarts need to be done, all homeworks need to be done. If you need help, and I'll check on that right after we talk.
Is this a long lab?
It is a bit of a long lab, yes. But if you've gone through it and looked at the procedure and sort of know what you're doing, you'll go better than if you try and just do it. Okay, any last minute questions? Okay, I'm planning on having Monday tutorial next week. I haven't put it up there. CE review. Okay, CE review for the test. So make sure by that time that you have your review done. Oh yeah, anybody this week?
Are you gonna be here after school?
Yep.
All the homeworks and smarts you do.
All homeworks and learn smarts up through chapter 6 are and include 6 are due by 15.
Is this like, is this gonna stay this morning?
That's just about it.
I think you have at 6 steps. I think 5 are due. The 6 are still in May. There's still a lot to be treated until like May.
Friday.
Yeah. It's like
I
Friday.
think everything is.
They fixed things for me, so when they fixed it, I said, make all of them happen and signed yet, do the last day, or whatever day in May it was. So, I'm really supposed to have you have it done by,
Okay.
but if it says
Well,
that.
because like the 5 ones is due January 15th.
They were all supposed to be there January 15th. I didn't get everything set, and then they screwed it up, remember? And everything was due January 15th. So, okay, time's yours. Let me know if I can help you. And I will look, it was 5, what were we looking at? 5A or yes? Was it 5A or yes?